Although most of our knowledge of the magnetic field is acquired indirectly, this is not an unusual route to understanding. Natural phenomena such as wind or rain are sensed directly as the strong blast of air hits our face, or the soaking rain covers our head. But we also identify these familiar processes indirectly as we look through a window and see a flag waving in the wind, or hear rain hitting the rooftop of our house. We know that there is a gravity field because its magnitude and direction are sensed as it pulls us down the stairs or restrains the weight we wish to lift. In contrast, we have no obvious body sensors that can respond to magnetic fields to tell us its strength and direction. The closest direct sensation of magnetic fields for us is the push or pull we experience when we draw two magnets close together. Since the development of simple compasses, the Earth's magnetic field has been an important aid for navigation, enabling travelers to find their way in uncharted regions. It became an essential tool in the exploration of the planet and facilitated the great voyages of discovery in the late 15th century that established links between the continents. It is one of the central properties of the Earth and has been studied with purpose-built equipment on land, at sea, and in the past half-century from satellites. The magnetic field extends far into space around the planet, where it interacts with the energetic particles from the Sun and interstellar space that impact on the Earth. It produces sideways forces on the rapidly moving, electrically charged particles and deflects them around the planet. In this way, the magnetic field acts as a protective shield against harmful radiation and enables life to exist on the planet. Several early pioneering studies contributed to understanding the magnetic field and the idea that it is a property of the Earth. In 1269, a medieval French scholar known as Petrus Peregrinus de Méricourt wrote a letter, called in short form Epistola de Magnete, to a friend in which he described experiments he had carried out on the magnetic properties of iron needles and lodestones. He observed that the magnetism of a sphere of lodestone, which he called a terrella, or little earth, varied over its surface but was concentrated at diametrically opposite points. He used the term pole, from the Latin word polus, meaning the end of an axis, to refer to these centers of magnetic force, and he noted that there were different types of poles at the opposing ends of the magnetic axis. He established that magnetic poles of the same type repel each other, whereas unlike poles attract each other. However, instead of recognizing the ability to align in the north-south direction as an intrinsic property of the magnet, he attributed it to a celestial cause, such as the influence of Polaris, the pole star. This notion was to persist for almost 3 centuries. There was little further advance in the understanding of magnetism or the magnetic field during the Middle Ages that followed. The north direction indicated by a magnetic compass and the true geographical north direction are not quite identical. The discrepancy is called the declination of the field. The earliest record, in 1088, of the angle of declination is attributed to Shen Kuo, a Chinese intellectual who was knowledgeable in many subjects. The declination arises because the magnetic poles do not exactly coincide with the geographic poles. The vertical plane that passes through the horizontal component of the field intersects the surface of the Earth on a great circle called the magnetic meridian. In 1576, Robert Norman, an English compass maker, showed that a magnetized needle that is free to swing in the meridian plane aligns at an angle to the horizontal. This observation appears to have already been made in 1544 by Georg Hartmann, a German instrument maker, but his result did not become public knowledge until it was discovered centuries later. The angle between the field and the horizontal is called the inclination or dip of the field. It is defined by convention to be positive when the field points downward, as it does in most of the northern hemisphere. Our deepest penetrations into the Earth have been little more than 10 kilometers, or roughly 0.2% of the Earth's radius, and that depth has been reached in only a few locations. Several methods have been developed in the effort to probe the interior of the Earth, including laboratory replications of how the Earth's increasing temperature and pressure with increasing depth are likely to affect the materials believed to exist at great depths, imaging of the interior with seismic waves from natural or man-made mechanical forces, and measurement and interpretation of gravity, heat flow, and magnetic and electrical fields. Geomagnetic measurements have been used in this regard for 3 centuries or more, but profound advances in observational and computational technology over the past half-century have fostered rapid growth in the breadth of applications and in the utility of the method. Studies of the magnetic field of the Earth's crust were originally used to locate hidden iron ore deposits and other ores associated with the highly magnetic mineral magnetite. Subsequently, the magnetic method has been used to map crustal geology, which has proven to be useful for petroleum exploration and environmental studies, for studies of the structure, thermal state, and tectonic history of the lithosphere, and for numerous other societal and scientific applications. The surface shell of the Earth, the crust, is petrologically and geophysically distinct from the underlying mantle. Characteristically, the rocks of the crust contain variable amounts of the mineral magnetite, which commonly produces a magnetic field mappable at the Earth's surface. The Earth's crust and the underlying uppermost part of the mantle make up the mechanically strong lithosphere, which is roughly 100 kilometers thick. The source of Earth's magnetic field lies in its deep interior, specifically within the liquid outer core composed predominantly of molten iron and nickel. Here's how it works. The geodynamo process. Heat from the inner core and lower mantle drives convection in the outer core. As this electrically conductive fluid moves, the Coriolis force, due to Earth's rotation, organizes the flow into spiral columns. These motions generate electric currents, which in turn produce the magnetic field, a process described by dynamo theory. Dynamical models show that as long as convection persists in the core, the magnetic field is continuously regenerated, counteracting the natural tendency for magnetic fields to decay through ohmic dissipation. Dynamo theory. This theory explains how the conversion of kinetic energy from fluid motion to magnetic energy maintains the field over geological timescales. It involves solving complex magnetohydrodynamic equations that describe the interplay between fluid motion, electrical currents, and magnetic fields. The magnetic field is generated by convection currents in the liquid outer core, which is composed mostly of molten iron and nickel. As heat from the inner core drives this fluid motion, the Coriolis force, thanks to Earth's rotation, organizes these flows into spiraling columns. This organized movement creates electric currents that, in turn, generate and sustain the magnetic field. This self-sustaining process is known as the geodynamo. Extending far into space, Earth's magnetic field creates the magnetosphere, a protective bubble that deflects most of the charged particles from the solar wind. This interaction not only safeguards our atmosphere from being stripped away, but also plays a crucial role in forming the Van Allen radiation belts, which trap high-energy particles. Earth's magnetic field is not only crucial for protecting our planet, but also serves as a window into the dynamic processes occurring deep within the Earth. Its study bridges geology, physics, and space science, revealing the interconnected nature of our planet and its environment.